Okay, so this is an application of linear algebra, and let's see if I can get this to work so it's a presentation mode. Okay, let's see. I think then, yeah, this will, okay, now I got the navigation right. Okay, so we'll go slowly because I want to sort of like help you understand it. There's a few questions about this on the application, but they're only like sort of more like reading questions than they are like actual doing anything. Okay, so epidemiology is sort of a mathematical modeling of epidemics, and one of the first models, I think this is from the 1930s, was the SIR model. And the SIR stands for the sort of describes the model in which you have a population of n individuals and you divide them into three groups, and the number of individuals in each group depends on time. So here's like you have susceptible individuals. That's this box here. So you have S of T. These people are not sick. They haven't been infected, but they can be infected. They're susceptible. You have the infected individuals, I of T, this middle box, represented here by there are people who have caught whatever the disease is, and they can infect others. And then you have recovered individuals who cannot infect or be infected, so they're out of the game. So these boxes sort of represent a room with all the people. Think of it like this. This is sort of the model. Now, what's going to happen is if everyone starts off being susceptible, and say one person's here, and that person may make other people sick, and so there's going to be some fraction of each time step. This depends on time. But they were discrete, like every month, every day, each time step, a certain number of susceptible people will get sick and move from this room to this room. And then for the people that are in this room here, well, a certain fraction of them, this fraction gamma here, fraction lambda here, will end up recovering and end up moving to this third room here. So think of it, so you can think of it sort of concretely in that form. And so this is the whole model. It's like basically no one dies, no one migrates. There's no, it's like a really simple model. And but it sort of has some interesting, results and stuff. Okay, so there's static assumptions that simplify the model. Okay, this is why I said the number of n is very large and does not change. So the number of the people in the rooms doesn't change. No one dies, no one's born, no one's fleeing or getting into the out. An infective individual becomes infective immediately, so there's no delay. You have to have more complicated models to deal with all these things. Also, everyone is mixing with everyone all the time. There's no geometry. It's not like people are spread out in space and there's some network of connections. It's like everyone's sort of this one big party. Okay, so those sort of set the background, simplify. But those are just sort of static. There's some dynamic assumptions, and these have to do with those numbers, L, lambda S, the fraction of people that are susceptible to get infected, and gamma I, the fraction of people who are sick who recover. In each unit of time, the number of newly infected this is the newly infected here. The fraction lambda is called the rate of infection. It's going to be a fraction, like 1/10, 1/4, and the SIR model. This is sort of a crucial thing about this model that makes it, actually defines what it is. Assumes that lambda is proportional to the fraction of people who are infected. Okay, so here's the number of people who are infected. Here's the total number of people. So this I over T is like half the people, 1/10 the people, 1/3 the people are infected. But that's sort of seems a natural assumption. The more people that are infected in the population, the more the lambda, the fraction that actually gets sick, is larger. So it's sort of like if there's more people who are sick, that means the fraction of people who this lambda will be larger. But it's modified by beta. So beta is bad for the population because the bigger, so if this was 1/10 and beta was large, it's going to increase the fraction. So beta is a characteristic sort of the disease itself. This is just this is sort of makes sense that the more people who are sick, the more people are going to get sick. But the beta sort of is like how bad the disease is. So this lambda here, now you notice right away, this I is one of the variables of the system. This S is the variable. So if I make lambda proportional to I, I've got two variables, I times S, which means this model is not linear as it stands. So it's not like directly, linear algebra is not directly applicable because this I here multiplies the S, so it's not linear. The second assumption is that the number of people who've recovered equals gamma I. That's this number here, The fraction gamma is called the recovery rate. The SII model assumes that gamma is constant. So that's an effect of a disease. It's just sort of like individual, sort of like everyone sort of has the same physiologies in this model. So they're all going to every time step, 1/10 of them, 1/100th of them are going to recover. So that's fixed because it's a property of the disease, whereas this is the sort of more of a property of the number of people. So this is the crucial sort of special thing here. This doesn't introduce this itself is a linear term. So it's this sort of assumption here that makes things a problem. And the whole deal is that big beta is this is a mistake here, a big gamma is good for the population because the quicker that people recover, right, the larger this gamma is, the fewer people who are infected. So the fewer people are infected, the fewer people are going to get sick in the next turn. So if you can sort of get people out of the infected thing quickly, but that depends on the disease. Okay, so that's our assumptions. And what we model, like most of the time, we have these are difference equations. Delta here means change it. I'm doing this because what you want to do is model differential equations are just equations that have different derivatives in them. And the whole point of differential equations is that you're modeling some system that changes in time, and you only want to look at local changes over a short time, and then somehow add up all those changes so that you want to look at small changes, which is what the idea of a derivative captures. So you can think of this delta as a very small change. It's just going to become a differential operator, like a derivative. But right now, so each time step, right? Each time step, which is delta t, right? Delta means the change in time here, the change in S. So we have a small change in time, we have a small change in S. So what this means is that this is going to be the change in the susceptible people who aren't sick. So it's negative because it's going to decrease because people are going to get sick. And so here is proportional to S. Here's this number lambda. Lambda equals beta I over n. That's the basic assumption. So it's decreasing by this fraction, which has the bad beta and the fraction of people that are sick. So you can see that for a given population size, the fraction of the total population that's sick is going to increase the number that gets sick. So this tends to decrease S. And if the only place these sick people can go is into the rim I. So this term is identical here because, except for a plus sign, because all the people who left S went to I and became infected. However, for I, there's also people leaving that room, which is minus gamma I delta T. So this is the change in I. And then the last one, R, the recovered, is just the people who left the infected room to the recovery room. It's just, this is a minus, this is a plus. So this is sort of captures the dynamics of people moving between those three rooms, or bacteria, whatever they are. Doesn't have to be, it can be, it's not specific to any particular organism or something for epidemics. Okay, so these are nonlinear equations said because you have variables R, S, and I. I times S, I times S. So there's the nonlinearity in there. Now, what we're going to be interested in situations where these are special situations where nothing changes. That's because what you want is you want the changes. It's a steady state. You want to know when there's no. This is sort of second when there's no disease propagating, right? Because if the susceptible population, some people might not have gotten sick, but no more. There's no one getting sick. There's no one who's infected that's recovering. So this represents a case where the disease is gone. Okay. Now it turns out that only changes in S and I are crucial because you notice that since R is equal to N minus S minus T, if you wanted to know what R was, the number of recovery, you just have to look at S and T. So R is just following along. So we can ignore R. We can ignore this because it's constrained. Whatever S happens to S and T, we can find R from that. So there's nothing new in R. So we can just take these top equations here, the top two here, look at them down here. They're just copied down here, except for the fact of two things. I've set delta S equal to 0 and delta I equal to 0 because this is the case for no change, right? Because I've set this is equal to 0 and this is equal to 0. So as a result, that also going to mean that R is equal to 0. But that means this is 0 and 0. So I can with this delta T, I can then move over here and cancel out, right? And then the delta T here, which multiplies both terms, I can get rid of. So I have just these differential equations. Okay. As my model. They're still nonlinear, but they're for an equilibrium situation. There's no general methods to solve nonlinear equations. This system is actually solvable, but there's no general. If you look at quotient differential equations, you'll have mainly linear differential equations, and at nonlinear ones, at certain places around equilibrium situations, we do what's called a linearization, which is what we're going to do here to find a version of these equations near the equilibrium point, so we can tell really close in, it's going to look linear. And then what we want to see is it tend to, if you make, it's sort of like if you imagine a marble in a valley, in a bowl, you can sort of, at the very bottom of the bowl, it's going to be just sitting there. And if you just take it a little bit, just not give it a nudge, it's going to roll away, but then sort of roll back and go back to the beginning. So that's stable. But if you put it on sort of like a tabletop or something like that and give it a nudge, it's going to like roll off the table. So it's unstable. Okay, so we want to distinguish between stable and unstable equilibrium here. And that's where we're going to go next to look at this. So here's these equations, right? Disease-free equilibrium states. This is just the copied equation. So these are, so if I can find S and I and T, these are equilibrium states. Now, if you have S equals 0 and I equals 0, this represents the endpoint after everyone has been infected and has recovered. So, for example, if there's no one susceptible and no one infected, then N equals R, because N equals S plus I plus R. So that's just what everyone got sick and it's over. Because, so that, of course, if the disease was bad, no one dies here, so it's not that bad a disease. But the point is, this is sort of like the worst case scenario in which everyone got sick, right? At least 100% of people, no one escaped. Okay, but however, there's another kind of state where you're interested in, where this is the equilibrium state before anyone has been infected, right? This is the disease-free equilibrium state here. So let's then look more at this thing here. So we want to do what's called, this is where linear algebra comes in. We want to know if this state here is stable or unstable. Okay. And so here's the linear stability analysis. This is where linear algebra comes in, and so it tells you what happens close to some state. If your system, you think of this marble on a bowl or on a hill, and this is stable and unstable. So linear algebra goes and looks really close in here, because really, if you zoom in, it looks almost linear. So as a result, that's what we're doing. Now, this is a technical thing that we have to do is we want to choose our S to be this is the number. It's going to be helpful to look at the number of individuals who are not susceptible. S is the number that are susceptible. S star is the number that are not susceptible. So if I take N minus S, I'm going to get S star. Okay, in this equilibrium state. So then the disease-free state occurs when S star equals 0, right? Because that's what we want. We want to have our equilibrium sort of have values of 0. So instead of having N here, we're looking at, since the S star is 0, that corresponds to S equals N. So this corresponds to the equilibrium state. And you notice that delta S star is minus delta S. So if the number of people who are susceptible decreases, this is an opposite change, because those people are becoming not susceptible because once they're infected, whatever, anyway. So what I want to do is go through and make this, whoop, I didn't want that. Let's see. It's a little bit too large, okay. Yeah, so what's going to happen is these equations repeated, but with where I put in S in the form of N minus S star. So I've just making a change of variable where I'm going to trade in my S for S star. So this equation is equivalent to this one, just adding S and subtracting S star. So I can plug in the S to get rid of it from these equations. So this is the original equation. So we're going to look at these things near S star equals 0, I equals 0. We're not going to be exactly there, but we're going to look at the number of individuals who are not susceptible in I here by doing this. And this is going to have some good effects, this change of variables, because let me go back. First of all, there is, when I put this in, you can see this N here cancels off this N here. It's not going to cancel off in the second term, okay? But it will cancel off in this first term. And so in the first term, I'll just have beta I N over N, so I'll just have beta I. With a minus term, will still be minus beta I S over N. And the same thing happens here. The N's cancel here, and you get that. So what's happening is that in these terms, we're going to use the fact that S star is very small. This is very small because N is really, really large. So we're going to neglect, just throw away the nonlinear term here, because we've gotten a remaining term here, which is the linearization of it. So this is see the N over N, and we've thrown away the nonlinear part, based on the fact that this term isn't proportional to N, whereas this term was proportional to 1 over N, and since N was very large, it's going to be very small, no matter what else is happening with I and S. So it's only approximation. It's only good when we're really close to the equilibrium points. But then these equations, this is the disease, this is near where S star is very small, okay? So as a result, because S is because you had S equals N minus S star, or S star equals N minus S. And if S is very close to N, S star is close to zero. So that's why these equations are linear equations, because the ends cancel. So I cancel the ends here and here. I end up with this set of equations, and they're linear equations in the sense that they're still differential equations, but they're linear equations in the sense that there's just an I here, there's an I here, and an I here. There's no products of terms. Okay, so here's our linear equations, in which they describe a nonlinear system near the equilibrium state. So that's their context. For small time steps, these become differential equations. Okay, in the sense that you have delta S star over delta T becomes S star prime of T, the derivative, and this becomes the derivative also. Now, it turns out these are first order linear differential equations. So if you look at this form here, it's like, think of the S star as just X. It's dx dt equals X. See, it's equals, the second one here is going to, well, let's look at the second one. The second one is di dt equals beta. I see this I dt on both of them, so I can get beta minus gamma times I. I'll repeat it over here, so maybe again, so you can see we'll have delta I delta t. So I divided this delta t by the delta t here and here, and that's going to equal. So this is the left-hand side. Now I'm doing the right-hand side. Well, I've got a beta from here minus a gamma from here. I'm going to factor out the I, beta minus gamma times I. Now this equation, if I this looks like an equation that you've seen before. If you have probably dx dt equals, say, just call this some number, n times, we'll call it r. R times x. Well, this says the derivative of this x is a number times itself. Now, if you plug in an exponential here, e to the rx, then you'll see the derivative of this function. When I take the derivative with respect to run our x there, sorry about that, of t there. When I take the derivative with respect to t, it's going to bring down an r and leave the x here. So you can just plug this in here and see that it actually solves this equation. The differential equations, of course, you learn that you can, if you can get a complete set of equations with functions like this sort of solves the system entirely. So what we're going to do is we're going to notice that if we put this in here, so that we have this, and we put this, so we some initial S naught times e to the RT, I is I naught times e to the RT. Since these are linear first order equations, we can actually just sort of guess the solution. That's what we're doing here. And we're guessing the solution because they're linear equations, and we're doing that to get a linear algebra problem that we want to solve to see whether the things are stable or not. Because what's crucial here is this R value, okay? So here's the derivatives of this where you take in ds dt. There's the R that's been brought down. So we have to find R. Okay, so if when I put these in this equation, what's going to happen is the e to the RT will be over here, and the e to the RT will be over here. So those will cancel out, and I'll be left with, after the e to the RTs cancel out, cancels, I'm left with these equations. So finally, after all this, we actually have a linear system. Okay, it's not quite in standard form, but we can put it in our standard form, right? So again, this is sort of like the process in which you'd make a model, you'd find the differential equations, describe the time development of the model, you'd find equilibrium positions, and then look really close in and find a linear system next to that equilibrium position. Then using the knowledge of linear differential equations, you can solve the equation like with some guessed solution or some solution method, and then find at the end that you've got a linear system that involves R. And these initial numbers, this is the S naught, I naught, the initial number at time zero. So this is this S0, I0 are time zero populations, okay? But then in here is R, beta, gamma, and beta. So it's clear that in an E to the R2, what's happening is this is either going to get really large or really small quickly. It depends whether R is less than zero or whether R is greater than zero. And we want to see what's the connection between R and beta and gamma. Remember, beta is bad population, but gamma is good, okay? So this is, if you look at this, here's S naught, I naught, 0, 0, beta, beta minus gamma, RR. If we put this into a matrix form, here's our linear system in a matrix form. Here's the coefficient matrix, 0, 0, beta, beta minus gamma. The two variables, S naught and I naught as a vector, R as S naught and I naught. And we should recognize this as an eigenvalue equation, right? Matrix times a vector gives a number times the same vector back. So this is your eigenvalue equation. Well, the eigenvalues are the things you want to know, because they tell you, the eigenvalues tell you whether the R is sort of like going to be stable or unstable. Okay, so we do this same procedure. We find we subtract the eigenvalue from this diagonal term, and we have a matrix. We take the determinant and find that it has two eigenvalues, R equals 0 and R equals beta minus gamma. R equals 0 is the less interesting. The first eigenvalue describes a situation which no one is infected to begin with, I naught equals 0. So, because if, on the other hand, though, R equals beta minus gamma is a situations where some people initially are infective, and the number of infected people then looks like this. Okay? So you can see that this model predicts a relation between R and beta minus gamma, which is the solution takes this to equilibrium. If beta minus gamma is positive, the number of infected people grows exponentially. That's unstable. And we define, instead of this beta minus gamma, it's usual to define beta over gamma. So you can see if beta is larger than gamma, so if this is R is larger than 1, then I decreases and we might have an epidemic, right? But if R naught is less than 1, I decreases, and that means that everyone's getting well. Well, this R naught is actually the R naught that you get reported, that you probably remember from reports in about the COVID, which was the fact that R naught, you can look back at the equation, so it was sort of the number of people infected sort of each time step or something. So basically it's a characteristic of the disease, because you can see beta here, which is bad so a big R naught is bad because beta is big. So in this model, this is sort of this ratio of the beta and the gamma, and this is what you sort of converted it like that. And let's go on and see. Okay, so there's the takeaway. From that, this is what the exact solution looks like for this model. If you can solve it exactly, that if R naught is greater than 0, what happens is, so this is if R naught is greater than 0 and you start up with a certain number of infected people, you can sort of see the total number goes to 0 over time. The N here increases, the blue is the number of recovered people, everyone gets sick, and the number of infected, so you have this little hump here that goes up and comes down. Because what's happening is there's lots of people, and the disease just gets more and more, and people are infected. But then the recovery gets to take in, so that takes more people out, and it begins to decline. Now, here's what happens if R is less than 0. You can see that not everyone gets sick, right? So if R is less than 0, the smaller it is, there's some people who got sick, but then it just declines smoothly, and the number of recovered people. So here, you want to obviously make this as fast as possible, or whatever. Anyway, these are the two situations that you have. Sort of, this is a really sort of a really, it's a really simple model, but the number are not sort of measurable. And for COVID-19, it was between 2 and 3. For the Spanish flu, it's about the same. 1.2 for Ebola is only 2. So COVID has about the same, had even a higher R naught than Ebola, and SARS had 3. So these are all comparable diseases, right? However, if you look at like some of these other diseases for which, fortunately, we have vaccines, R naught 6, chickenpox is 10, measles is 15. What that means is that one person who's sick tends to infect 15 other people. So if you have a kid in a classroom that's sick, measles is so infective, all you need is like 1 or 2 time steps or 1 or 2 kids infected, and you get the whole class of 30 people infected. So what's going to happen is then these high R diseases, because they're so infective, methods that are sort of only partially, like masks, quarantine kind of things just don't work because nothing's ever perfect with masks and other stuff. So that it's just so infective that the only hope is vaccines. And this model doesn't take into account vaccines, but you can make other models that do. And so you have to get so then you have other reproduction rates with vaccines, and that, so you have some hope as long as the quarantine methods sort of work down in here, but they're hopeless up here. So there's a big changeover here in these R values and anyway. So there's sort of things to think about. This is what epidemiologists do, is they make more models, like age stratified models, geometry. So they'll have models that instead of like a 2x2 matrix, they might have a 10x10 matrix. But it's a really complicated system, and they do the linear stability analysis, and then do everything on computers. Anyway, but that's sort of the sort of beginning model that was developed when epidemiology was just getting started. And you can see that this R naught is directly connected to sort of a measure of an eigenvalue that you found with the linear stability analysis. And so linear algebra is one of those tools. Okay. Well, that is